This is the lecture for Friday, April 3rd. We will be continuing our discussion of quantum chromodynamics. Today we'll be talking about vector mesons, we'll talk about quark confinement, and we'll talk a bit about baryons as well. So vector mesons, remember mesons are these combinations of a quark with an antiquark bound together in a hadron that's colorless. And so the vector mesons have the total spin of 1, and in the simplest picture of a vector meson, the quark and the antiquark have no orbital angular momentum. They just sit on top of each other. And so all that spin is coming from the intrinsic spin of the quark and the antiquark. Okay, so the quark has intrinsic spin 1/2, the antiquark has intrinsic spin 1/2. You add them together, and you can have spin 1, and that's what happens with the vector meson. Okay, so these vector mesons are more massive than the pseudoscalar mesons we talked about before, like the pion. And the pion had the pi plus, pi 0, pi minus had a mass of about 130 or 140 MeV. These have much larger masses, so let's talk about them. So the K star 0 has the structure where you have a down quark and an anti-strange quark, and has a mass of 896 MeV. The K star plus has a U and an S bar, and this has a mass of 892. Then we have the 3 rho mesons, the rho minus, the rho 0, and rho plus. These have masses of about 775 MeV. And so the rho minus is du bar, and the rho 0 is u bar minus dd bar with a factor of 1 over square root of 2 for normalization. And the rho plus has a structure ud bar. I'll come back to the omega and phi in a moment. And now the K star minus has a structure of su bar, and the K star 0 bar has the structure sd bar. And these have the same masses as this one's 896, and this one has mass of 892. Now, the omega has the structure of a u bar plus a dd bar. So this has there's a factor of 1 over square root of 2. This has a mass of 775 MeV. And the phi meson has the structure S bar, and this has the heaviest mass because the strange quark has the heaviest mass of all 3 of them. And so that mass is 1019. So if we have the quark and the antiquark, there's some potential between the two. And what you find is that the potential appears to be linear in the distance between the two, between the quark and the antiquark. Okay? And so it looks something like this. Here's the potential versus distance of separation. Let's say r is the distance between the two. You have this linearly rising region here. At short distances, it's different than that, but as you pull further away, you find that you get this linear behavior. And this is also seen in simulations, lattice quantum chromodynamic simulations, lattice QCD simulations, where you put a quark here and let's say an antiquark there, and you see a little tube. So here's a plot of what's called the color electric field. And so what you see is here's for the quark and the antiquark, and you get this flux in between the two. And the formation of this thing, what's called a flux tube, is what's giving rise to this linear region here. Another consequence of this is that, oh, by the way, I should mention that sometimes you hear the terminology that the QCD vacuum acts like a dual superconductor. Just like with a superconductor, a superconductor tries to expel out the magnetic fields. I'm not sure if you're familiar with that, but it prevents the magnetic fields from entering through a superconducting material. Okay? So this is what's called a dual superconductor, in that it expels the color electric field, the quantum chromodynamic electric field. So what it's essentially trying to minimize the region in which the color electric field is non-zero. So that's why it sort of tries to narrow the range and narrow the coverage of the the color electric field, and that's why it's compacted into this flux tube. Another way to see this confinement is to look at the masses, or actually here is plotted the mass squared versus the angular momentum for a family of mesons. And what you find is here's the row, here's what's called the A2, the row 3, and you find these straight lines that appear, these families. And that can be described in terms of some sort of a flux tube model again, and so some sort of like a rubber band picture between the quark and the antiquark. And these are what are called Regge trajectories, and the theory behind this is what's called Regge theory. And so it's simply just describing, again, a linear rising potential. I should mention, though, that this old, what's called Regge theory, is the precursor to what developed into string theory. Now string theory was developed to try to explain this string, or this flux tube between the quark and antiquark. But as you probably know now, string theory has developed into possibly a description of the theory of everything, that fundamental particles are made of these strings. But originally, this whole idea of string theory was to describe these flux tubes. So here's another picture then of the formation of this flux tube. So outside here is the QCD vacuum, the ground state of the system, but between the quark and the antiquark there's this formation of an color electric field. And so as I pull these apart, you get this flux tube forming. Okay, here's a picture of exactly that. We have our quark and antiquark. We pull them apart and we get this flux tube. But eventually we pull them hard enough because it requires energy to pull them apart, and we get this potential energy. It eventually gets strong enough, large enough, that it's energetically favorable for a quark-antiquark pair to appear out of the vacuum here. And so instead of being able to pull the quark and antiquark apart from each other, you don't succeed. You simply create another pair of quark-antiquark, and so you end up with two mesons. So that perhaps should remind you of what happens with a magnet. If you have a magnet and you try to, you have a magnet with a north and a south pole, and you try to isolate the poles from each other, and you cut the magnet in half, you end up having simply two magnets like this, rather than getting these individual poles of a magnet. The same thing happens here with these mesons, because of quark confinement. Now here's another sketch. This is sort of an artistic rendering of what's called a glue ball. That you have these glue balls, the gluons that are sticking to each other and forming a colorless object. I have to admit, I don't really see the symbolism of this drawing, but that's what it's supposed to represent. You can also have this thing, what's called a hybrid meson, where you have then quark and antiquark pair, just like you have here, but there may be some admixing of glue balls or glue-like states here. That makes it more complicated. These are called hybrid mesons. So now let's turn our attention to baryons. So baryons have three quarks, like the nucleon, the proton or neutron. Okay, so each of these quarks, there are three possibilities for the light flavor. So we're talking about up, down, and strange. Okay, and so we're going to do the SU3 analysis here. So we have three. That's this representation for either it's UD or S. We have cross 3 combining with another light quark with another light quark. So 3 times 3 cross 3 cross 3. Okay, and this composition, I'm not going to derive this here, but you end up getting in SU3 representations, irreducible representations. You get a 10-dimensional representation, an 8-dimensional one, another 8-dimensional one, and a 1-dimensional one, what's called a singlet. And this is what's called a decouplet. This is again an octet, but this is what's called a baryon octet. Okay, this is another octet, and this is a singlet, just from the names, from the numbers. Decouplet means 10. Okay, a grouping of 10. All right, this S stands for the fact that under the exchange of the labels U, D, S, that the SU3 flavor symmetry, it's symmetric. It's completely symmetric under interchange. These M's stand for the word mixed, meaning that they do not have, they're neither symmetric or antisymmetric, but something in between. And this singlet here is antisymmetric, so it's completely antisymmetric under interchange of the flavor labels of this baryon. Interchanging whether you have an up with a down, it's changing up with down, and so on. Okay, so let's consider this guy, this baryon singlet. So this baryon singlet has isospin equal to 0, and it has this structure to it. This is what's called the lambda, and this is UDS plus DSU plus SUD minus DUS minus USD minus SDU. So as promised, it should be antisymmetric under the interchange of these labels. So if I interchange the DU with the D here, I get the DUS, but there's a minus sign here, so you see that it's antisymmetric. Okay, so now the color and flavor wave function should be antisymmetric, and thus it turns out for this case here, the zero orbital angular momentum doesn't actually work, and also spin 1/2 are not possible if the wave functions are to be overall antisymmetric. So what you actually need in this case, you need a little, because the symmetries don't quite work out, you actually need in this case, for the spin 1/2 case, you need to have orbital angular momentum to make the Fermi-Dirac statistics to work out. And so in this case, to get the lambda, what's called the lambda 1405, you need to have the spin has to be 1/2 parity minus, and so we need to have an L equals 1 state, orbital angular momentum. If we go now to the decouplet state here, this one has 10 particles, 10 baryons. So we start off with the strangeness 0, so these have no strange quarks, the DDD, UDD, UUD, and UUU. So we have the delta minus, the delta 0, the delta plus, and the delta double plus, or delta plus plus. And then if we have one strange quark, that's strangeness -1, we get the sigma star minus, sigma star 0, sigma star plus. Now if we have, so that's DDS, UDS, and UUS. If we have strangeness equals to -2, you have 2 strange quarks. And so we have the DSS, that's the Xi, what's called the Xi star minus, and the Xi star 0. Now if we have strangeness equals to -3, all of the quarks are strange quarks, and this is what's called the omega minus. So these guys have angular momentum 3/2, spin 3/2, with positive parity. Now, as Gell-Mann was writing down all these structures, these group theory structures, it turned out that this omega minus was, this omega baryon was not discovered, so he could make a prediction of the existence of this just from this pattern, that there was something missing, and that was actually a pretty big deal. So Gell-Mann made this prediction. He predicted what the mass was from the patterns of the masses that you're seeing here. There's sort of like a very simple relationship that the masses then go from here to here. They go up by some set amount. They go up again by some set amount, and then again by some set amount. And so you can predict the mass of the omega minus particle. And so he made that prediction in 1962, and it was then discovered at Brookhaven in 1964. And they agreed quite well. So let's go on and talk about the baryon octet now. Okay. So let's talk about the familiar baryon octet that we get that includes the neutron and proton. So we have neutron, proton here. You have the up, down, down, and the up, up, down. Okay. And so now, but they also, so the masses are 939.6 and 938.3 MeV. But then we also have these hyperons that are part of the baryon octet. And so then we have, here's the sigma minus, okay, sigma 0 and sigma plus. They have one strange quark. Okay, so DDS, UDS, and UUS. Let's come back to the lambda 0 in just a moment. And then we have the Xi minus, and the C0, which is DSS, and the USS. Okay, so you can see the patterns of the masses, the increases here. These guys are about 1,190 or so, or 1,115, and these are larger, about 1,320 or 1,315 MeV. Now this lambda 0 has also a structure UDS, and it has a mass of 1,115. Okay, now if we want to try to construct the wave function and at the simplest level, so remember quantum chromodynamics is really complicated, so this is just the simplest wave function we can write down, where the proton has no orbital angular momentum. You're making that assumption. The quarks are just sitting at the origin, let's say. Then you can write down a proton wave function in which you have complete anti-symmetry because they're Fermi-Dirac statistics, right? So you have something like this that you could make that would be completely anti-symmetric. So you have you have an up quark with up spin, down quark with down spin, and then then that has would also come up. You would also have an up quark with an up spin, a down quark with a down spin, and an up quark with an up spin. But you see what you've done is you've changed these two guys. Okay. Now you'll notice here that the wave function is actually symmetric under the interchange of the flavor, the ups and the down labels, and the spin labels. So that's what you construct here. Now, the reason why it's anti-symmetric though overall is because when you look at the color description of the proton wave function, it's completely anti-symmetric under the red, green, and blue labels. And so just to recap, what I'm saying is with respect to flavor and spin here, where it's completely symmetric, but then the color comes in, it's completely anti-symmetric, and that saves the day. We can also now take a look at the magnetic moment of the nucleon. So here we are actually making an approximation, what's called the quark model approximation. And I have to make an omission that the quark model is something that works, but we don't really understand why it works. Okay, what you do is you pretend that the quarks, which actually have a small mass, we'll talk about that in a moment, but the quarks actually have a mass that's on the order of, let's say, 300 MeV, which they don't, but let's just assume that they do. And then you have these relatively heavy quarks that just sit there with some spin, and so then you have some baryon with three quarks, and then you can determine what the magnetic dipole is from the quark structure of these what are called constituent quarks. Right, in this quark model picture. And you can do that, so you can write down what the magnetic moment is in terms of the quark magnetic moments. Okay, so if you make the assumption that the up and down quark masses are equal, then you find out that the magnetic moment for the up quark then would be equal to -2 times the magnetic moment for the down quark. Right, simply coming from the fact that the magnetic moment here, okay, is going to be proportional to, you'll have a factor of the charge, and so because the up quark, charge of the up quark is 2/3, and the charge for the down quark is -1/3, and so that's why the magnetic moment for the up quark is -2 times that for the down quark. All right, you can go through now and write down these various combinations for the proton, so you get 4/3 again, we're just doing the simple quark model picture, adding the magnetic moments for the quarks. You get 4/3 magnetic moment for the up quark, -1/3 magnetic moment for the down quark, and then for the neutron you get 4/3 magnetic moment for the down quark, -1/3 the magnetic moment for the up quark. And you can go through and do this for a whole bunch of different baryons, and you find that you make predictions that are really quite good. You make a best fit with a few unknown parameters for the magnetic moments for the quarks. You just fit that, and then you find that you're in really quite good agreement with experimental data, right? And you can even predict, for example, that the magnetic moment for the neutron over the magnetic moment for the proton should be about minus 2/3, about minus 0.667. And so it comes out that experimental is minus 0.685. There have been many people who have tried to explain this from some simple picture of why this should work, but I have to admit, this is something when I was a graduate student, I wanted to try to explain, but I did not come up with a good description of why this should work, why the quarks end up behaving like they're heavier than they really are, and more weakly interacting than they really are. So in real life, in the real universe, in reality, these quarks are really light, and they have these interactions through the gluons that are very strong. But you can somehow pretend that they're heavier and more weakly interacting, and you come up with this beautiful description that works, but nobody understands why. So that's a puzzle. Now, we can expand this out by also including Tromp quarks. So if you include Tromp quarks, then we not only have this baryon octet that we just described for the neutron, proton, and the sigmas and the lambdas and the xi, minus, and 0. We can add a Tromp quark and go through sort of into this three-dimensional picture where we add one Tromp quark or two Tromp quarks. Okay, we can also take the baryon decouplet, the 10-dimensional representation, and add Tromp quarks as well. And so you can do it like this. Now I have to admit that this sort of classification scheme, you can use this to classify the particles, but the symmetry, the approximate symmetry that you might expect to get by expanding this SU3 now becomes an SU4. This does not work very well because the Tromp quark is quite a bit heavier in mass than the other quarks. All right, so but still you can use this to try to classify the particles. Now you can even go further and then include the bottom quark as well. All right, and then it's difficult then to draw the picture here because it would be in another dimension as well. Now, I'm going to finish talking about then this particle which is called the Roper. The Roper resonance is, as far as we know, can be thought of as the proton's first radial excitation. So it has the same quantum numbers as the proton. It's spin 1/2 with positive parity, okay, and isospin 1/2 as well. Now here then is the mass of the Roper. So remember the mass of the proton is 938, MeV. The Roper is 1,420 to 1,470 MeV. It has some width to it, so there's some uncertain. There's some There's an imaginary part to the mass if you want. It's unstable particle. It's a resonance. The Roper though it's somewhat puzzling in that so it decays into it can decay into a nucleon. That's what the capital N stands for, plus a pion. That's what it does most of the time. But it also can decay into some other things like nucleon with 2 pions and so on. Okay. Now the Roper though turns out to be rather sorry, I should be pointing here. The Roper turns out to be rather difficult to reproduce. A lot of calculations that have been done, for example, with lattice quantum chromodynamic simulations, tend to overestimate the Roper mass. There have been some studies to try to understand what might be causing this. Here you can see one possible explanation is that the lower than expected mass is due to some sort of dressed quark core, all right, shielded by a dense cloud of pions and other mesons. I'm not sure why the Roper is lower in mass than the lattice quantum chromodynamic simulations, but I assume that these simulations will eventually be able to get better to describe this Roper particle. And here is now just a picture of the color electric flux that we get then from the 3 quarks from, let's say, a nucleon. Okay, and so we get this sort of like Mercedes-Benz kind of a structure to it, this 3-pronged star. And so again, the flux tube is trying to minimize the space that it occupies, and so you get sort of this vertex here where the flux tubes connect together. All right, so now here's now another picture of these sort of well, these are just the pretty pictures of the gluon field. Uh, Here you see a quark-antiquark being created out of the vacuum, all right? And so here I'll just read it. A quark and antiquark pair created from the gluon field is illustrated by the green, anti-green, or magenta quark pair on the right, all right? And these quark pairs give rise to the meson cloud around the proton. Now, let me just stop here, and I should mention this puzzle. Well, actually, I'll go one slide beyond this, since it's connected to this slide. If we look at the mass, right, of the proton, okay, so we know that the mass of the proton is 0.938 GeV, all right, and so that's kind of surprising in that the mass of the up quark is about 3 MeV. Okay, the mass of the down quark is about 6 MeV, or 0.003 GeV, 0.003 GeV, and 0.006 GeV. And if you add these numbers together, you're nowhere close to 0.938 GeV. So where does the rest of the mass come from? Okay, and where it comes from is actually all that gluon interactions between the quarks. Remember, I drew this picture. You have your 3 quarks, and then you have gluons doing all kinds of crazy things. You can also have a virtual pair of pair production, and so these gluons are actually producing that extra mass. So one can talk about the quarks getting some mass from the Higgs mechanism. That's something we discussed in connection with the weak interactions. The Higgs particle actually gives these quarks their masses, okay? Without the Higgs particle, they would be masses. But there's also a mass coming, an effective mass coming from QCD, so that, again, here's the picture, sort of like the constituent quark I was talking about. Somehow, these guys are behaving like they have 300 MeV, and so that's what the constituent quark model is all about. You give these masses about 300 MeV, 300 MeV, 300 MeV, and then when you add them together, you get about 900 MeV mass for the proton. But how this all happens is very complicated, and that's where the domain of lattice QCD comes in to try to understand this. So you can try to probe this by measuring the correlations between the correlation function. Meaning, what you do is you create a quark here, and then you try to destroy the quark at some later time, some operator. Okay, so you create a quark, and then you let it propagate, and you try to find how this propagation changes as a function of the separation or time. Actually, what you do is you evolve, and you create the quark at one time, and then you destroy it at another time, and then you look at how this amplitude changes as a function of the time separation. All right, and you can then read off the mass of the constituent quark by looking at this quark correlation function. And what you find is something that looks like this. This is done using calculations from what's called a Dyson-Schwinger equation. What that is you just simply solve a bunch of, for a sum of a bunch of Feynman diagrams using some recursion relation. I'm not going to give the details here because it's a bit complicated. Or you can do these calculations using these lattice QCD simulations. And so what you find then is that at large momentum, at high energies, these quarks are very small. The masses of the quarks are small. But at low momentum, what you get is an effective mass that increases. So this is the idea of how these quarks behave like constituent quarks, and they have a much larger mass than they should. So I'll stop there, and I hope you all have a good weekend, and we'll finish quantum chromodynamics on Monday.